it is visible. So let's introduce Dr. Sachidananda Prasad. He is an accomplished electrical engineer with a strong academic background and significant professional experience. He received his BTech degree in electrical engineering from GHITM, Puri, India in 2007, followed by an MTech in power system engineering from VSSUT, Burla. He completed his PhD in electrical engineering at the National Institute of Technology, Warangal, India in 2018. With 11 years of teaching and research experience in reputed universities, Dr. Prasad has made noteworthy contribution to the field of power systems. He worked as an associate professor and HOD of the Department of Electrical Engineering at NIST University, Odisha. He has been recognized for his research, receiving the prestigious POSCO Power System Award PPSA in 2018, the doctoral category, awarded by Power System Operation Control Limited POSCO, in collaboration with the Foundation for Innovation and Technology Transfer FITT at IIT Delhi. Additionally, he was conferred with the PPUT Foundation Day Research Award in 2023 for being the best researcher of the year in electrical engineering by PPUT Rourkela. Dr. Prasad has published several research papers in esteemed journals such as IEEE Transactions, IET, and Elsevier, focusing on areas like distribution system, automation, smart grid, and the use of artificial intelligence technique in power systems. Currently, he serves as the principal engineer in SurrEnergy India Private Limited. Here he continues to apply his expertise in advancing the field of power system studies. Over to you, Dr. Sachidananda.
Thank you, sir. Thank you for the introduction. Am I audible, sir?
Yes, yes.
Okay.
You're audible.
Thank you very much, sir. Thank you for the brief introduction. First of all, I would like to thanks to the organizer team, department and institute, the Department of Electrical Engineering, PMSC Barampur, for giving me this opportunity to present a talk in this Atal FDP program on mitigating climate change through sustainable electrical engineering solutions. So let me go to my presentation, PPT. Is it visible to all of you? Please respond. PPT is visible.
Yes, it is visible.
Okay.
Yes,
okay.
please.
So my topic of discussion will be grid impact studies for the grid connected solar PV system. What are the different studies we need to conduct for a grid connected solar PV systems for ensuring reliable and stable integration of solar PV system into a grid. So these are my contents of my presentation. First, I will introduce, then grid code, why we are going for the grid code, why you are referring grid code, then what are the need of power system studies, what are the objectives, what are the different components of power system studies, overview about the grid connected solar PV system. I will take one case study to discuss different types of power system studies which are conducted before installing a PV generating plants. So the title of the FDP is mitigating climate change through sustainable electrical engineering solutions. As you know that climate change becoming one of the most important topic of discussion in recent years, and due to the continuous use of fossil fuel based energy systems and the petrochemical based transportation system, the effect of climate change can be observed, and we need to go for best sustainable solutions to overcome this climate change effect. So which can be particularly you can observe the effect of climate change in the field of energy sector. because since long time we are using fossil fuel based energy resources, and due to which you can observe the temperature effect, the pollution, all these things are coming into picture. So therefore, one of the best solution we can say the renewable energy based power generation. And so therefore, whenever a RE generator, a RE developer, renewable energy developer is going to install a PV plant, and which needs to be connected to the grid. So what are the different studies he has to uh, conduct? He has to conduct that I'm going to discuss here. What are the different studies, grid impact studies the RE generator has to, RE developer has to conduct, and he has to submit all the system studies report to the utilities company for its approval. And after getting the approval from the utilities, you can say central transmission utilities or POSOCO, then only the plant can be charged to the grid, can be connected to the grid. That means the PV plant can be interconnected to the grid. So what are the different studies need to be conducted? So that I'm going to discuss in this presentation. So grid impact studies are the analysis, different analysis to be conducted to evaluate the effect of connecting new power generation. Suppose we are going to connect a solar PV system or wind generating systems to an existing electricity grid, then what are the different studies we need to take care, so that we have to ensure that the system will be stable, reliable, and operates more efficiently after the integration of the new asset. That means when you are going to integrate the PV system, we have to ensure that the system will be stable, reliable, and operates efficiently. And these studies we have to submit to the utilities. So the key objectives of the grid impact studies are assessing grid stability. That means the systems when we are integrating the PV plant to the grid, uh, because of the integration, it should not create any kind of issues or instability issues like voltage or frequency instability. So those issues should not be created because of the injection of the PV at the uh, grid bus. So evaluating the thermal limits also. So you have to check whether the transmission lines, the conductors, the cables, or the transformers, whether they are violating the thermal limits. That we need to produce a report and we need to submit it for approval. And a reactive power becoming one of the most important challenge, and voltage control at the grid bus. That means our interconnection point, which is called a point of interconnection, POI. At the POI, we need to check all these things. That means to analyze the performance of the uh, plant. So we are taking a reference point, that is our point of interconnection. So there we are evaluating whether the plant is maintaining the power factor 0.95 leading or lagging or not. So that we have to verify by conducting reactive power uh, analysis. Similarly, harmonics and power quality study also to be conducted, because as you know, PV plants are we are using inverter based renewable sources, IBR system, inverter based resources. So basically, since due to the presence of inverters, which are power electronics based converters are there, so therefore there is a possibility of injection of harmonics into the grid. So that percentage, how much it can be, how much percentage of harmonics distortion, THD value of a current harmonics or voltage harmonics can be injected. So according to the guidelines, according to the IEC guidelines, we have to follow. So before interconnection, these are the, therefore these are the study we are conducting. Then protection system coordination. That means how to because of the short circuit, different kinds of fault when occurs in a system. So how to use protection coordination system, how you are coordinating the relays, the circuit breakers from downstream network to upstream network in a PV system, so that the system will be should not the components what we're using, the equipments what we're using, that should not get damaged because of a because of any short circuits or events happened into the system. So that's why protection coordination system also one of the most important study need to be conducted. before interconnection. Then contingency analysis, as you know, that if suppose a different line outages or generator outages, line outages, transformer outages, these things will happen into a system. Then what is its effect? Which of the lines, which of the transmission lines will get overloaded? Which of the transformers will get overloaded? That we need to investigate by conducting contingency analysis. And compliance with the grid codes. So basically, before going for the interconnection, we have to produce the grid compliance study also. So I will briefly I will explain each and every studies need to be conducted before going for interconnection of the PV plant to the grid. So first we have to know what is grid code, because we need to fulfill the requirement mentioned in the grid code, Indian grid code. So it is nothing but the rules to be followed when connecting generators to the grid. So whenever we are going to connect an external asset like PV generators, solar plant or wind plant, so we have to follow some rules. What are the rules need to be followed for connecting the grid, that is specified in the grid code, Indian uh, uh, grid code. So it is basically issued by the TSO, transmission system operators, and the main purpose is to ensure the system stability and reliable operation of the system. And RE generators must comply with the grid code. So what are the grid codes are there for each study that I will introduce while during my discussion, topic of discussion. And grid codes for renewable generating are still evolving. As you know that the rules are revising based upon the recent situations. What should be the, when we are integrating the sources, what challenges and about how to overcome it. And most existing grid codes have similar general requirements. Basically, we have, you can see the different countries grid code, like European grid codes, Germany grid code, Indian grid code, South African grid code. So they are the different country based grid codes are there. Suppose you are getting a project from different countries. So first we have to check what is the grid code they are following, because you need to analyze the whole system. Uh, you need to do all these studies based upon the grid code of that country. Suppose we are going to install a PV plant in India, then we have to refer the Indian grid code, technical standards for connectivity to the grid, published in 2013, and amendment published in 2019 by Central Electricity Authority, CEA. So we have to follow the CEA guidelines. So when we are going for the grid connected solar PV system, so first we have to take the reference as a point of interconnection. What is the point of interconnection point? That means the point of interconnection of a renewable energy generating station with the grid. What is the bus at which you are going to inject the PV generators? Okay, so that is the point of interconnection, and which is considered to be the reference point where all the studies had to be assessed. So in this figure, you can see the ISTS substation and dedicated transmission line is there. Then generating pulley station is there. That means the power evacuation will be taking place at the PY point, power evacuation. That means how much power you are generating using solar or wind. So that will be evacuated at the interconnection point. Okay, so through transmission lines. Transmission line generating pulley stations up to this part will come under the RE generators. And here we have to fulfill at the point of interconnection, we have to fulfill all the requirements by the according to the Indian grid code. So main objective of the study is to assess the impact on grid stability and performance. The system has to be stable. If you are integrating the PV plant to the grid, so because of the interconnection of the PV plant, the grid should not get disturbed. So that you have to ensure that the system, the grid will be stable if you are integrating the PV plant into it. So therefore, we are conducting all these studies, and a report has to be submitted to the grid utilities for its approval. And after getting the approval only, then only we'll go for first time charging of the PV plant. and ensure compliance with the grid code requirements. As I said, we have to follow the grid codes for different kind of studies, and we have to ensure also that it is following all the grid code rules. And we have to optimize the design for reliability and efficiency. So you have to optimize the PV plant design for its reliable operation. So they are the different components of grid impact studies. That means what are the different studies need to be conducted whenever you are when a RE developer is going to install a PV plant. Okay, so first is load flow analysis, which ensures the proper voltage levels, evaluates power losses and transformer overloadings, voltage at all the buses are within limits or not, within suppose pond 95 to 1.05 per unit voltage or not, you are able to maintain or not at all the buses, and what is the losses happening, and then transformer overloading case also, cable overloading case also. So that can be ensured from the load flow analysis. So therefore the energy consultant has to conduct the load flow analysis, power engineer has to conduct the load flow analysis, and the report has to be submitted. Then next important study is short circuit analysis. I will discuss each and everything in details by considering a case study, a practical case study I will consider, and I will explain how the things are happening. Then short circuit analysis. Short circuit analysis basically when we are going to integrating a PV plant to the grid. Then if suppose short circuit happened, three phase short circuit, or line to ground fault happened, or double line to ground fault, double line to line fault. If these type of faults will happen, then what is the maximum short circuiting current will flow to the PV system? Okay, so what will be the fault contributed by the grid? What will be the fault contributed by the PV plant? So those things will be investigated so that the breaker will be designed. What is the circuit breaker? What should be the size of the circuit breaker? What should be the size of the circuit breaker? What should the types of protecting device need to be connected so that the system will be protected if short circuit happens. So we have to produce, we have to so you have to go for a short circuit analysis, and we have to produce a report and submit it to the utilities. Okay, so I will consider a practical case studies, and I will conduct a short circuit analysis also. What are the important parameters we need to check during short circuit analysis. Then reactive power analysis, one of the most important task performed by the consultant, and that is reactive power analysis. That means to maintain whenever you are supplying, you are generating PV electrical power through PV generators, and you are injecting it to the grid bus at the interconnection point. So in order to maintain 0.95 power factor lagging and leading at the point of interconnection, how much reactive power needs to be injected, how much capacity of a capacitor bank or STATCOM or SVC should be connected at the PV end, so that the power factor can be maintained at the POI. At the POI, these are the guidelines of the CA regulations, according to CA regulations, and which we need to follow. Okay, so therefore at the point of interconnection, you have to maintain 0.95 lagging or leading. Power factor should be 0.95 lagging or leading. So these are the two extreme situations. So you have to decide how much the capacity of the reactive capacitor banks need to be connected at the inverter end, at the inverter station, to maintain the power factor at the POI point. So that's why we are conducting reactive power analysis also. Then harmonic analysis or power quality test. Basically, as you know, since we are using power loopings based inverters, so obviously there is a possibility of harmonics generation, voltage harmonics and current harmonics injection into the grid, and there is some acceptable limits according to CA guidelines, so which we need to follow. So that or based upon the harmonics generation, we have to decide what should be the size of the filter, active or passive filter. So what should be the size of the active or passive filter needs to be installed at the inverter station, so that the harmonics can be reduced, total harmonic distortion can be reduced, because of the harmonic injection, more heating effect will be produced, more losses will happen into the system. The waveforms will get distorted because of the harmonics, and as well as basically this is coming under power quality test. Under power quality test, we are conducting harmonic analysis, DC injection analysis, and flicker. Okay, so these three studies are coming under power quality test. So that has to be conducted. And then dynamic and transient stability analysis. Basically, the transient basically whenever suppose you are going to integrate the PV plant to existing plant. Suppose the existing plant is having a number of generators will be there. Already a plant is existing where number of synchronous generator or diesel generators will be there, and you are going to integrate the PV plant to the existing plant. So then because of the integration of the PV plant to the existing plant, so whether at the point of interconnection, you have to check, you have to analyze the transient stability analysis. Because of the integration, because of the fault happened and the PV end, whether the generators are stable or unstable. So what should be the, what are the different types of faults you need to apply at the PV end, and you have to check the generators which are there in the existing plant, it should not get disturbed, or in what kind of fault the generators are getting unstable. So that is also coming under the transient stability analysis. And whenever suppose if you are connecting the PV plant to the grid at the grid bus, then you have to follow some other kind of dynamic studies like LVRT test, fault ride through test, low voltage ride through, high voltage ride through. Those tests we need to conduct to check that if suppose a fault happened at the grid side, then voltage will goes down to a very low value. So since voltage is going down to a very low value at the point of interconnection, at that time you should not, the PV generator, PV plant should not get disconnected from the grid. So up to what time it has to be connected to the grid, and suppose voltage is getting higher. So our limit is 0.95 to 1.05. Suppose it is going 1.3 per unit, 1.4 per unit, 1.2 per unit. So up to what time the PV plant has to be connected with the grid? It is not that if it is just crossed 1.05, the plant has to be disconnected. Okay, so those things, those are those analysis will be coming under dynamic study, and in briefly I will explain. And then last one is protection coordination study. So as I already said, so you have to go for the relay coordination study whenever you are installing a PV plant. So what should be the size of the circuit breaker? What should be the size of the, what is the relay? How to coordinate the relay so that whenever a fault will happen into the system, then minimum part of the system can be disconnected instead of disconnecting the major part of the network. So proper relay coordination has to be done for smooth and reliable operation of the PV plant. So one by one study I will discuss. So as I said, and I'll also talk about what are the different softwares being used at the industry level to go for load flow analysis. What are the softwares used? What are the standard follow for load flow analysis, for short circuit analysis, for reactive power analysis, dynamic study. For different studies, what are the standards need to be followed, and what you have to ensure in each analysis. So load flow analysis, as you all of us know, it is a steady state analysis performed, and to know the voltage, current, power, and losses into a system, and whether voltage at all the buses are within limits or not. Suppose you are connecting the PV plant to the grid at the PV plant end, at all the buses voltage should be within the limits. Okay, and the transformer should not get overloaded. The IDT transformer, basically we are using inverter based transformer. So IDT transformers we are using. So that should not get overloaded. What should be the rating specified? So those things can be verified by conducting the load flow analysis. Okay, and what are the different tools we are using? We are using PSSC tool, ETAP, Dixel, and Power Factory. These are the different power system tools software tools we are using to conduct the load flow analysis. And the standard we are following is IEC 399. This is the standard we are following to for load flow analysis. Okay, so voltage profile you have to check at the point of common coupling, PCC or POI point, then flow distribution, active and reactive power distribution of the solar PV system to the grid, then loss calculation and system planning. Based upon that, to evaluate the impact of varying solar generation. That means different case study you have to perform. That means when the plant is generating its full capacity at a zero power factor, because inverter can be run at a different power factors. A range will be provided from 0.8 to 0.8 to lagging to 0.8 leading power factor. So within that, various you have to create various operating scenario, like when the PV plant is generating 100% its capacity at the unit power factor. Okay, similarly at 50% generation, unit power factor, 10% generation, unit power factor. So different case study you have to create, and you have to analyze the system when the PV plant is integrated to the grid connected system. Because sometimes because of the cloud, your generation will get reduced. So that case study also you need to perform. That means when the generation will be very, very low, that time what will be the effect produced into the system. So when the plant is connected to the grid. Okay, so they are the softwares we are using. So they are the different case study. I can say maximum generation conditions, minimum generation condition, varying load demand. If load changes for different operating scenario, loading, you have to conduct load flow analysis. Then for maximum generation condition, 100% generation suppose, and suppose you are looking for the 10% generation, 25% generation, a different generation level, you have to perform the load flow analysis. So I have considered a case study, a small plant I have taken, 10 megawatt plant, 10 megawatt DC capacity, but its AC capacity is 8.25. Okay, so this is the description of the network. The PV plant, 10 megawatt PV plant is connected to the grid, the power grid at 33 kV bus. At 33 kV bus, the PV plant is connected. Okay, and where one IDT transformer is there, inverter duty transformer is there, which capacity is 8.25 MVA. So why 8.25 MVA transformer is connected? Because the DC capacity is 10 megawatt, but actual AC capacity is 8.25 megawatt, 8.25 MVA, you can say. Okay, at unit per factor. So 8.25 MVA. So so therefore, a small plant I have considered, only one single one inverter duty transformer is required, 8.25 MVA, and it is a 3-winding transformer. So primary side is 33 kV, secondary side is 0.8 kV, 0.8 kV. Two LV panels will be LT panels will be there, and voltage level is 0.8 kV, 0.8 kV. Okay, so it is basically it is a 3-winding transformer, and percentage of impedance is 11.5% at the rate 4.5 MVA base. Okay, and it is a DY11. Most of the we are using a DY11. Primary side is delta, secondary side is star connected, and ON, AN, and OCTC will be 2.5. 5% at the rate 2.5 steps. That means 2 steps will be there, 2.5 into 2, 5% step changing. Okay, and percentage of tolerance considered is 10%. So, and inverters, you can see who I make model. The other OEM, you will get it from the OEM, originally in equipment manufacturing data sheet. So, and the other breaker details are also important for short circuit analysis. So therefore, here I'm specifying, and I'll show you the circuit also to explain how to design a PV plant using a software. E-type software I will show you, and how the load flow is conducted. Just one single line diagram I will show you, and where we have conducted all the studies, load flow analysis, short circuit study, and then reactive power analysis. Okay. So there are the different case scenario to perform the load flow analysis for a 10 megawatt solar PV plant. There are the different case scenario we have considered. Case one is a load flow analysis for existing plant with a 10 MVA DG without solar PV plant. These two cases I have not considered. The third case I have considered to explain, that is load flow analysis for 100% solar PV generation, and RPCD with inverter at unit power factor. RPCD means reactive power compensating device. a capacitor bank or a SPC or a STATCOM we have connected at the inverter station to maintain 0.95 lead or lag power factor at the POI. Okay, so what should be the capacity of the RPCT that we have to decide. And this is the case study we have considered, I have considered, and based upon which I will show you the ETAP simulation results. And basically, we need to perform all these case studies. If you are going for this load flow analysis of a PV plant connected to the grid, so you have to go for 100% generation at a unit power factor, 50% generation at a unit power factor, 20% generation at a unit power factor. So they are the different case study, and you have to observe the behavior of the plant when it is integrated to the PV system, grid. So here you can see the ETAP simulation. We have considered a small 10 megawatt plant. I think let me expand it. Mhm. Just a second, let me. Okay, yeah. Is it visible to all of you? Please respond. Is it visible to all of you? Am I audible? Hello?
Yes, yes, it is visible.
Yes, yes, yes. Here you can see, yeah. So this is the grid bus, POI, 33 kV bus bar. This is the point of interconnection. This is the bus at which the PV plant is interconnected. And this is the 33 kV grid bus. And basically, whenever you are going to connect the PV plant at a grid bus, so you must have to get the what is the MVAC, what is the short circuit MVA rating of the grid bus, and what is the ampere in kilo ampere you will get it, what are the X by R ratio, those information will get it from the utility. That means at the grid bus, at the point of interconnection, what is the MVAC, grid MVAC. So that information we need to put it at the grid bus, because this is simulated in ETAP software. So this option will be provided, a grid option will be provided, and where you need to put those values. What is the kV in kV, 33 kV. This is the 33 kV grid bus. You can say the point of interconnection, and MVAC is 914.523. It will be specified, it has to be specified by the utility. Okay. Or in terms of ampere rating or X by R ratio or MVAC, those information you will get it from the grid, because you are going to inject the PV plant at this grid bus. Okay, so this is called grid bus, and these are the two existing. This is existing plant, existing. Um, this is you can say that this is the load end, 5 MVA, 5 MVA. That my total generation is 10 MVA. So two 5 MVA transformers are installed at this bus, and below you can see the plant. You can see this is the PV plant. So I will go down. So this is the PV plant. So as I mentioned, that one IDT transformer is there of capacity 8.25. Here you can say this is a IDT transformer of capacity 8.25. Okay, so this is a 3-winding transformer, and we have modeled the solar plant. So in this solar plant, there are 30 string inverters are there. These are all in string inverters. 30 string inverters, and each inverter capacity is 275 kVA. So 275 into 30, you will get it the total capacity of the plant. Okay, so this is the capacity of the each inverter is 275 kVA, and this is the PV panel, and this is the DC bus. So a PV panel is connected to the DC bus, then DC bus is connected, the inverter is connected to the DC bus, because inverter will convert the DC into AC. Then it will be connected to the AC bus which is called inverter bus. Then inverter bus will be connected through a cable to the LT panel of the IDT transformer. So these are the two LT terminal buses. Two buses are there. 0.8 kV buses are there. So similar, the since it is a three winding transformer, so two LT panels are there. So in each LT panel, there are 15 number of inverters are there of capacity 275 kVA. Okay, so 15 plus 15, which is 30 into 275. So this is the total kVA rating of the PV plant at around 8.25 kVA. So now this ITT transformer rating is 8.25. Okay, so we are conducting the load flow to check whether the transformer is getting overloaded or whether which cables are getting overloaded, what is the voltage at all the buses, that we need to verify, and which is called the load flow analysis. Whether are the PV plant, this is, they are the two LT panel buses, this is the RMU bus, 33 kV skid RMU bus. This is a skid solutions actually. So this is a 33 kV RMU bus because transformer is converting 0.8 kV to 33 kV. So it is connected to the 30 kV RMU bus. Then this is connected to the switchboard. This is a 33 kV above, a 33 kV bus is there. And then a transmission line is connected, and at both end of the transmission line, two underground cables are there. Then it is connected to the POI, point of interconnection. So up to transmission line, you can see here, up to grid bus, this is RE generator has to take care. Okay, so you have to maintain 0.95 power factor. You can see here 0.95 power factor, 95.1% power factor. Okay, that means you have to size the capacitor bank which is installed at the PV station. What should be the size of the capacitor bank needs to be connected at the PV substation, so that MV station, so that 0.95 power factor lagging can be maintained. Because you need to supply reactive power to the grid. You need to supply you should not absorb reactive power from the grid. Okay, unless it is instructed by the utilities. So therefore you need to the are the extreme situations you have to take care how much reactive power needs to be connected here at the PV end, so that 0.95 power factor can be maintained at the point of interconnection. So that is the task performed by the power engineer. So, here you can see the transmission line. What is the loss happening in the transmission line? What is the voltage drop in the transmission line? Okay, and what is and here also we can vary the inverter power factor to meet the required power demand at the point of interconnection. So therefore, we are conducting in order to know the total losses in a system, in order to know the voltage profile at all the buses, of the PV plant, whether it is within limits or not, whether any cables or transmission line is getting overloaded, that needs to be verified by conducting load flow analysis. And therefore, we are conducting load flow analysis using different softwares. And according to the CA regulations also, for each analysis, what are the softwares needs to be used for its approval. So you can conduct the test using PSSC software. You can conduct the test by using E-type softwares. So based upon the different grid code, according to different countries grid code, so you have to use those softwares to conduct the analysis. Otherwise, it will not get accepted. So particular softwares, what is mentioned in the grid code, that need to be used for the analysis of the various studies. So this is about load flow analysis, and this is one small plant. I have a 10 megawatt plant. This way we are simulating and analyzing. This is small plant. Similarly, 400 megawatt, 500 megawatt plant needs to be simulated and analyzed, and the report has to be generated and needs to be submitted to the EPC contractor. Actually, the utility, the RE developer, he has to hire a EPC contractor, and EPC contractor will hire a consultant, energy consultant, who will perform all the studies. And the role of the EPC contractor has to uh, collect all the analysis report from the consulting engineers and submit it to the utilities for its approval. This is the process when you are taking any studies at the plant level. So moving to the next slide. So this is also, this is I have shown you in terms of different options are there. This is the losses in kilowatt and kVAR. Previous one what I shown the circuit that is specified in kVA in terms of kVA, ampere and power factor. This is specified in kilowatt and kVAR. That means at the point of interconnection, how much real power you are injecting. You are generating 8.25 MVA, but you are injecting 7.8 megawatt at the point of interconnection. Okay, so suppose you need to maintain at a POI 8.25 MVA, the contract demand. What should be the, though the plant capacity is 10 megawatt DC capacity, but actual AC capacity is 8.25 MVA megawatt. But how much you are injecting at the point of interconnection? Suppose 7.8 megawatt. So either if, you have to see what is the contract demand at the point of interconnection. If it is 8.25, then you have to decide what should how much extra inverter I need to install at the plant so that I can maintain the contract demand. Okay, so so those kind of analysis we are conducting during load flow. Okay, so next this is load flow analysis, and then we are going for the short circuit analysis. So second one is, as I said, what are the different components of grid impact studies? What are the different studies we are conducting? So first one is load flow analysis to know the status of the network at the steady state point. What is the status of the plant? Okay, so then we are conducting short circuit analysis. This is also one of the most important analysis conducted by the consultant to know whether what are the protecting devices we have considered into the plant, whether all are the ratings are okay or not, that we have to check it. So by conducting short circuit analysis, what is the short circuit? Suppose one three-phase short circuit will happen into the system, then how much maximum short circuiting current will flow through a line, through the cable, through the power transformer, through at the PV end. So that we need to investigate. And what is the fault current contributed by the grid? Suppose a short circuit happened, then what is the fault current contributed by the grid? What is the fault current contributed by the PV plant? That things we have to observe. Then we have to decide what should be the rating of the circuit breaker, what should be the rating of the CT, PT. Everything will be decided after conducting the short circuit analysis. So that's why whenever you are going for the installation of a PV plant, the basic preliminary analysis to be done is reactive power analysis and short circuit analysis, because short circuit analysis will decide what should be the grounding systems will be designed based upon the short circuiting current. Okay, so you have to first consider, we have to go for short circuit analysis, three-phase short circuit, line to ground fault, double line to ground fault, double line to line fault. All the cases you have to consider into, and you have to analyze how much maximum short circuiting current, what is the minimum short circuiting current. We are calculating the maximum as well as minimum short circuiting current. So whenever here I have shown you, here I've written also, this analysis helps to design protective systems, verifying equipment ratings, and ensures overall system stability and safety. So therefore, this analysis is conducted. And whenever a fault happened into the system, short circuit happened into the system, so this is the waveform of the current. You can see the waveform of the asymmetrical waveform of the current. And basically, we are measuring the initial symmetrical short circuiting current. What is the initial symmetrical short circuiting current? IK double dash. You can see here written IK double dash. Okay, what is the value of the IK double dash that we are first calculating for different kinds of fault, like three-phase short circuit, line to ground front, LG, double LG, LL. For each case, what is the IK double dash, symmetrical short circuiting current? Because based upon the IK double dash, the breaker rating will be decided. Okay. So this is IK double dash, which is nothing but the RMS value of AC symmetrical component of a prospective short circuiting current, and applicable at the instant of short circuit if the impedance remains at 0 time value. Okay, so this IK double dash value we are calculating, and this is according to IEC 60909. This is the standard we are following when you are conducting the short circuit analysis. IEC 60909 standard we are referring, and we are calculating what is the initial symmetrical short circuiting current, what is its value. Okay, and whether suppose you have to consider a circuit breaker at a particular feeder, and the short circuiting current in that filter is more than the breaker rating, then that breaker capacity is not acceptable at all. So you have to go for higher rating. So that's why we are conducting short circuit analysis to know how much maximum short circuiting current will flow through a feeder line into a PV system. And this is the mathematical relation of IK double dash C into UN divided by root 3 into JK, and where C is the voltage factor, equivalent voltage factor. We used to use 1.1 for maximum short circuiting current and 0.95 for minimum short circuiting current, because you have to conduct both a maximum three-phase short circuit and minimum three-phase short circuit. Maximum line to ground fault, minimum line to ground fault, maximum double line to line fault, minimum double line to line fault. Maximum LLG fault, minimum LLG fault. Why minimum short circuit test is also conducted? Because when you are going to do the relay coordination, the coordination of the protecting devices, that time we are setting the relay setting based upon the minimum short circuiting current, not maximum value. For a reliable operation, for make it more sensitive, we are setting it at the minimum level, not at the maximum short circuiting current level. Okay, so therefore, when you are conducting the short circuit analysis, at the time you have to consider both the cases, maximum short circuiting and minimum short circuiting cases. Okay. So there are the different types of faults: three-phase fault, which is more severe, and a single line to ground fault, line to line fault, double line to ground fault. And what are the inputs required for this study? Single line diagram of the system, a PV plant single line diagram. When it is connected to the grid, that input has to be you must have. Then equipment data, various types of equipments we are using in a PV plant: transformer impedance, generator parameters, line impedance, etc. Source impedance, utility grid or generating unit. That means whenever the PV plant is connected to the grid, what is the X by R ratio or MVAC rating that has to be produced by the utilities. Okay, so then only you can conduct the short circuit. Otherwise, you cannot know what will be the short circuiting current contributed by the grid. So that information has to be produced by the utilities. Okay. So we are calculating the symmetrical and asymmetrical components of fault currents. IK double dash particularly we are measuring at a different buses, at a different feeders. And this is the standard we are using, and basically the software which is being used is ETAP, PSCAD, PSSC, and Dixel and Power Factory software. These are the power system softwares we are using to conduct the short circuit analysis by referring IC 60909 standard. Okay. And the application is sizing of circuit breakers and fuses, setting relay protection, and identifying the weak points in the system. Basically, to decide what should be the size of the fuse or circuit breaker, MCCB, that has to be decided based upon the short circuit analysis. Okay, and setting relay protection. That means when you are going to coordinate the relays, protecting devices. So at the minimum fault current levels, we are fixing it. So therefore, you have to conduct the short circuit analysis. And when you are going to integrate a solar PV system into the grid, so this has to be done. The same system I have taken. You can see the same system. What I 10 MVA system. So PV plant, 10 MVA PV plant. So the rating of this is a circuit breaker, VCB circuit breaker, which is basically used for a high voltage system. Vacuum circuit breaker, 33 kV, 630 ampere, 25 kilo ampere for 3 seconds. Okay, so they are the ratings of this vacuum circuit breaker, and so at solar PV plant, LV circuit breaker, ACB, air circuit breaker of having 4000 ampere at the LT panels. Okay. So this is at the low voltage level at 0.8 kV, we are using ACB and MCCB, but at a high voltage level, we are using vacuum circuit breaker, VCB or SF6 circuit breakers, basically used for high voltage systems. So the same plant I have considered and conducted the load flow and short circuit study. Here you can see a three-phase fault happened, and how to know how much fault current is contributed by the grid into the plant. Okay, and what is the size of the bank you have? What is the size of the CB rating? You have considered that you need to verify it. You can see. I think it is visible to all of you. Here you can see a three-phase. So in E-type software, those options will be there. So you have to use it. And let me expand it to show you what is the short circuit contributed by the grid. Here you can see 33 kV grid. The MVAC rating is 914.523 MVAC short circuiting current. And whenever a three-phase short circuit happened, the short circuiting current contributed by the grid is 16 kiloampere. So 16 kiloampere of a current, fault current will be flowing injected into the at the point of interconnection due to grid. Okay, so that will be specified. And you can see here at different buses what is the short circuiting current. You can see uh, the bus where the PV plant is injected. You can see what is the at the 33 kV bus. You see what the fault current. So this is important. This is important task we have to follow. Just a second. Yeah. So because the rating of the circuit breaker will be decided based upon the short circuit test. So therefore, we need to check at LT panel. Suppose at LT panels, two LT panel, because this is a three winding transformer, how much a short circuit current is flowing. So that you need to see. So let me show you. This is not three-phase short circuit. I think I came down. Let me show you. Yeah. Yeah, this is three-phase short circuit. Result I want to show you. Here you can see just let 6.661 at 33 kV. Okay, what is the short circuiting current of this bus? Because we need to see also what is the bus bar short circuiting current withstand capacity. Bus bar rating also you have to check. That whenever you are going for a aluminum bus bar, what is the short circuiting rating? And whenever suppose three-phase short circuit will happen or line to ground fault will happen, double line to ground fault will happen, whether the short circuiting current the current of the fault current is exceeding the short circuiting current capacity of the bus bar, that you need to check it. Otherwise it will damage the bus bar. So therefore we are conducting the short circuit test to know to verify the rating of the bus bar, to verify the rating of the circuit breaker, to verify the ratings of the uh, line cables and all. Okay, so therefore different case studies has to be performed to verify the ratings of each components. Okay, so what is the short circuit current contributed by the inverter, that also you can see here. So these are the short circuit analysis. So what are the case study you have to perform? That is uh, uh, yeah, you can see here maximum I have in tabular form I have shown you maximum short circuit fault current summary for 10 megawatt solar PV plant. You can see the equipment. What are the different equipments we have considered? 33 kV aluminum bus bar is there. Skid RMU bus is there. 33 kV bus bar is there. This is the particular 33 kV bus bar is the point of interconnection. And IDT LV panel 1. This is two LV panels are there for IDT transformer, because this is a three winding transformer. So what is the at the LV panel? What is the short circuiting current? When there is a three-phase fault happened, what is the short circuiting current at these buses? You can see 7.274 ampere, kiloampere. It is in kiloampere. 7.131 kiloampere, 16.793 kiloampere, 30.426 kiloampere. When line to ground fault will happen, what is the fault current at in kiloampere? So based upon which you will decide what should be the breaker rating, or whether the short circuiting withstand capacity of the bus bar is exceeding the short circuiting current level, or it is within limits. If the short circuiting current is exceeding, then you have to use different ratings of software bus bar to withstand that short circuiting, because if short circuit will happen, so that much current will be injected. So you have to have that component to withstand that current. So therefore, we are conducting this test, and we are verifying. Finally, we are providing a report that it is compiled, that complied. Selected circuit breaker rating. What is the circuit breaker rating connected at this bus? 16 kiloampere for 3 seconds. It withstand capacity is 16 kiloampere. It can withstand for 3 seconds. Okay. Similarly, 25 kiloampere for 3 seconds, 20 kiloampere for 3 seconds, 50 kiloampere for 1 second, 50 kiloampere for 1 second. Basically, at the low voltage buses, LV panel, the time considered is 1 second, and the ratings will be very, current rating will be very high, because at the LV panel, the short circuiting current will be very high. And at HV side, the short circuiting current rating will be very, it will be very low. You can see also, you can verify also for 33 kV buses, the short circuit, three-phase short circuiting current is 7.274 ampere, 4.541 ampere, which is very, very less as compared to the LV panel bus. So therefore, you need to design, based upon which you have to design the circuit breaker rating at the LV panels and at the 33 kV buses. So therefore, short circuit test is conducted. And this is minimum. So minimum short circuiting current, this is required. Minimum value also required for the relay coordination study. So therefore, we are conducting maximum as well as a minimum short circuiting current. And this is all about the load flow and short circuit analysis of a solar PV plant when it is integrated to the grid, and what are the parameters you need to take care at what point. And why we are conducting these two tests. Then third test is the reactive power. Just briefly, I'm explaining all these tests and why it has to be conducted. Reactive power analysis of a grid connected solar PV plant. That means when a PV plant is connected to the grid, so you have to conduct this test also, reactive power analysis also. Okay, so that means because to avoid the voltage instability issue at the point of interconnection, you must have the reactive power compensating device at the PV substation, PV station, PV station, so that you have to maintain the power factor according to CA regulations. According to CA regulations, you have to maintain the two extreme situations, 0.95 lagging to 0.95 leading. So they are the two worst case scenario. So that's why you have to perform the reactive power analysis at these two worst case scenario. They are the two worst case scenario. 0.95 lagging to 0.95 leading power factor you have to maintain at point of interconnection. Okay, so how much reactive power support you must have at the plant, at the PV plant, so that you should not violate this criteria. So therefore, we are conducting reactive power analysis at the point of interconnection. Uh, so when you are going for the reactive power analysis, you can see reactive power capability curve. Okay, so which is the most important thing, reactive power capability curve of the PV plant at the point of interconnection. This is one of the most important task you have to verify. Okay, whether it is whenever you are going to plot this PQ capability curve of the PV plant at the point of interconnection, so that curve has to lie outside this boundary. The shape you are seeing, it is V shape. The PQ capability of the PV plant, whenever you are going to plot the PQ capability curve of the PV plant, you are connecting to the grid at the point of interconnection. So that curve has to lie outside this V curve. Then you are fulfilling the requirement of the CEA at point of interconnection. So if it is coming inside of this V, then you are violating the limit. So you have to decide what should be the size of the capacitor banks you need to connect at the PV end, so that you can complied by the CA regulations. So this is one of the most important tasks performed by the consulting engineer to verify whether we are able to maintain 0.95 lag and lead at the point of interconnection or not in those two situations. Okay, so how much reactive power support you have to provide at the point of connection. So this test basically conducted using ETAP software or Dixel and Power Factory software we're using to conduct this test, and based upon which you have to give a solution to the EPC contractor, that you can go for SBC or STATCOM. As you know, that capacitor banks, STATCOM and SBC, they are the compensating reactive power compensating devices which are presently available, and the most dynamic performance is STATCOM performance is better than the capacitor banks and SBC. So what should be the size? And as you know, you very it is a very serious issue that you have to do this test so accurately that the accurate size of the STATCOM you need to find, because the cost of a STATCOM per MVA is very high. Okay, if you are increasing the size of the capacitor bank or size of the STATCOM, the cost of investment will be more. So you have to optimize the size of the STATCOM or SBC or capacitor banks. Okay, so accurate value you need to specify by conducting this reactive power analysis test. So what exactly we are doing in this test? According to CA regulations, you can see this table CA regulations on technical standards for connectivity to the grid. Okay, for RE generating stations. RE generating means renewable energy generating station, PV plant. When PV plant is going to be connected to the grid, so you have to follow these CA regulations. That means the other test you need to conduct when voltage at the PY is 1 per unit, and you have to provide unit power factor. Okay, so at the point of interconnection, what is the power factor? 0.95, that means at a unit power factor, at 0.95 lagging, to maintain 0.95 lagging, how much reactive power support is required? To maintain 0.95 leading, how much reactive power support is required? Okay, for at various voltage level at the grid. That means when grid voltage is maintained at the point of interconnection is maintained at 1 per unit, then what's to have 0.95 lagging, what should be the size of the capacitor bank? What should be the size of the reactive power compensating device? That you need to analyze by performing this test. Okay. So therefore, this is the CA regulations, and this report you have to perform this task. All these cases you have to run and produce the report and submit it to the utility grid, and then need to verify it whether you have that capacity or not, whether you have accurately determined the capacity of the reactive power compensating device or not. So those things has to be verified, because of the PV plant, when it is connected to the grid should not get disturbed. Your PV plant should not absorb reactive power unless it is instructed by the grid utilities. So you should always supply reactive power to the grid. You should always supply reactive power support to the support at the point of interconnection. So you should not absorb it unless it is instructed by the grid utilities. So that we need to verify it by conducting this test. Okay. So therefore, we have to follow the CA regulations, and while conducting each test, and the standards we are following to conduct each test. And sometimes you can get the support reactive power support. That means you can utilize the reactive power support from the inverter end also, because inverter also can support reactive power to the grid. Though you should have a balance, you should have a compromise solution between the rating of the capacitor banks or STATCOM or SBC along with the inverter support what you are getting for reactive power. Inverter can also supply reactive power, but you have to control the power factor of all the inverters. So if you will suppose running the inverter at 0.95 lagging, 0.95 lagging or 0.9 lagging or 0.96 lagging, you have to see what should be the, if inverter is able, because that also depends upon the what is the contract demand. You need to fulfill the contract demand at the point of interconnection. How much real power, how much active power you have to inject it to the grid. So first, your objective is to fulfill the reactive power, real power demand. Then reactive power can be adjusted by taking the help from the inverter of the PV plant, and also the SBC or STATCOM or capacitor bank installed at the PV plant. But you need to decide if you are going to, if this much of contracted power I need to maintain at the point of interconnection, then what should be the power factor of the inverter? All the inverter has to run at what power factor? Okay, and if this is the power factor of the inverter, then what should be the size of this STATCOM? Minimum, so what the optimum size of the STATCOM or SBC or capacitor banks I need to install at the PV plant to fulfill the requirement at the grid bus. Okay, so that analysis we need to perform to verify to finalize the size of the capacitor bank or reactive power compensating device at the PV end, so that because of the PV plant, the grid should not get disturbed. The PV plant should not absorb reactive power from the grid. Otherwise, you will get a voltage imbalance and at the grid end. Okay, so therefore reactive power analysis study is performed. This is also one of the important tasks. So the other data means a PV plant SLT, you must have grid parameters also, then operating scenario. Okay, and different softwares we can use: PSSE, ETAP, and Dixel and Power Factory software. More efficient softwares specified by the CA according to CA regulations we can use, and according to grid code also. According to it, it will vary, depends upon the country grid code. Okay, so different softwares they will mention, they will specify. Suppose you are doing a project from United UK based project or African based project or Saudi Arabia based project, then based upon that you have to follow the grid code, and what is the software specified, that you have to use it to produce the report. Okay, so that's why for each case softwares will be specified. These softwares you need to perform the task. Okay. Simulation, basically reactive power analysis is nothing but the load flow analysis only, and you have to conduct the load flow analysis only for reactive power analysis, and voltage analysis test you have to conduct whether you are able to maintain voltage at the point of interconnection or not. Okay, so these are the solutions: compensating devices we are using, capacitor banks, STATCOM or SVC, and sometimes you are using tap setting transformers also to adjust the voltage. Okay. And then next study is power quality analysis. Third one, power quality analysis. Just briefly, I'll tell you due to shortage of time. So this is also one of the most important tasks performed by a power engineer whenever the RE developer is going to install a PV plant which will be connected to the grid. So at the point of interconnection, how much harmonics you are injected into the grid, that has to be verified. A report has to be generated. How much voltage harmonics, how much current harmonics, and what the DC injection, how much DC current you are injecting to the grid, and what is the flicker, what is the voltage flicker, what is the allowable percentage. So those things according to CA you have to verify it, whether you are satisfying all the terms specified in the Indian grid code, so that you have to justify at the point of interconnection. Okay, so therefore we are performing a harmonic analysis to evaluate the impact of a harmonic distortion caused by the inverter and other components of the grid connected solar PV system. And basically the power electronics devices will create the distortion in the power system. The harmonics are injected due to the power electronics devices, some nonlinear loads also, and because of the transformer operating scenario also, at what point the transformer is operating. Okay, so because these are the sources of harmonics, and therefore we are conducting harmonics analysis, and you have to get it approved that it is within limit. If the current harmonics, voltage harmonics, total TST at the point of interconnection, you need to report it, how much it is, what is this percentage, whether it is lying within 5% or not. This is according to CA regulations. Or that is also voltage harmonics, depends upon the voltage level, at what voltage level you are injecting the power to the grid, and what are the voltage level, 33 kV, 69 kV, 220 kV. So that according to that, the percentage of a THD will be decided and is specified by the CA regulations. So and you should have within that limit, then you will get the approval. Okay, so all the cases you must have to get the approval, then only you can go for the interconnection of the PV plant to the grid. Okay, so as you know that harmonics can lead to power quality issues, equipment damage, and a non-compliance with the grid standards. Okay, so we have to compliance with the grid standards. What are the grid standards specified in CA regulations that we have to comply by doing? Otherwise, things will not be approved. Okay, and then a DC current also, which should not be more than 0.5% of the full rated output at the interconnection point. It should not be more than 0.5% at the point of interconnection. That you have to take care. Okay. Similarly, flicker generating stations shall not introduce flicker beyond the limits specified in IEC 61000. So these are the standards we are following. IEEE standard 519 for harmonic analysis, IEC 6100 for a flicker analysis. So this is power quality analysis at the point of interconnection, and you have to generate a report for power quality analysis of a grid connected solar PV plant and submit it to the CTU, the utilities, for verification, for getting approval. So if you are following, you are complied by the grid code, then you will get the approval, and you will get the permission to go for interconnection of the PV plant to the grid. And these are the limits, voltage distortion limits as per the IEEE standard 519 2024. And the voltage, if your voltage point of interconnection at the point of common coupling, if voltage is less than 1 kV, then total distortion, acceptable distortion is 5%. And total harmonic THD, individual harmonic. This is individual harmonic because harmonics orders are starting from second harmonics to up to 50th order. So this is called individual harmonics. At the individual levels also you have to check what is the percentage of second harmonics, voltage harmonics, what is the percentage of uh, third harmonics, fifth harmonics, seventh harmonics, up to 50th harmonics. And the source what you are using, in the original OEM data sheet, you will get the harmonic harmonics report of the solar inverter. So that you have to use it as a input data to find the total harmonics injected at the point of interconnection. Okay, so therefore you must have the original equipment manufacturer data sheet while simulating the SLT in ETAP or Dixel and Power Factory software. So that is the most important text. That means whenever you are going to purchase an inverter, so in the data sheet it will be specified that what is the test report, harmonics test report you should have, and you will get it from the OEM dataset. So that report has to be used as a for input for the harmonic analysis. That means source harmonics, how much source is generating harmonics. So that you have to put it as a input, and then you have to run the harmonics load flow. Basically, we are running harmonics load flow to investigate what is the total harmonic distortion at the point of interconnection. So you need to conduct the harmonics load flow, which is available in the Dixel and ETAP software. Okay, and when your point of interconnection is 1 kV to 69 kV, the individual harmonics, that means starting from the second order to 50th order, it has to be less than 3%. And when you are calculating the total harmonic at the point of interconnection, it has to be less than 5%. So you have to take care, and this will be verified whether you are satisfying all the condition of the CEA regulations or not. Okay. Similarly, for 69 kV to 161 kV, if it is more than one voltage rating at the POI is more than 161 kV, then individual harmonics has to be less than 1%, and it has to, and the total harmonic distortion at the point of interconnection will be 1.5%. Okay. So similarly, flicker also, which is nothing but the voltage fluctuations, and specified in terms of long term and short term flicker severity. For MV system, it is 0.9, 0.7. It will be, you have to find it out. You have to, in software, this facility will be provided to run the flicker analysis, and it has to be within 0.9 or 0.7, depends what would be long term and short term flicker severity. You need to find it out. So these are the, according to the standard, they will verify whether we are fulfilling all the terms, conditions of. So these are the things we need to follow, and so we have to ensure that it is following the grid compliance and grid standards, IEC 519, IEC 6100. They are the standards it has to satisfy. And suppose how to mitigate the flicker effect, harmonics effect, by installing the harmonic filters. And you have to, based upon the percentage of harmonics, you have to decide what should be the size of the filter. what should the size of the filter also, it will be decided. Okay, and they are the key sources of the harmonics: inverters, transformer, nonlinearities, grid impedance, and loads. Basically, nonlinear loads will be available, due to which harmonics will be injected. Okay, and these are the harmonics sources which are available, and they are the standards you have to follow, softwares you have to see, use Dixelant Power Factory, MATLAB, also ETAP, PSCAD. At the industry level, we are using Dixelant and ETAP and PSCAD, EMT simulation tool. These are the softwares we are using. Dixelant Power Factory, ETAP, and PSCAD simulation tool we are using to conduct the harmonic analysis. And then the dynamic studies, just briefly, I'll tell you about dynamic studies. As you know that whenever you are going to integrate the solar PV plant to existing plant where diesel generators will be available, then you must have to conduct the transient stability analysis. So that means when the generators which are at the existing plant will be there, and now you are going to integrate the PV plant at a bus of a existing plant. Okay, so then because of the integration, there will be a chance of the generators will get unstable. Instability issue may arise because of the integration of the PV plant to the existing plant where diesel generators are available or synchronous generators are available. Number of synchronous generators will be there. So therefore, you have to conduct the transient stability analysis, which is a dynamic study. You have to perform by simulating the PV plant along with the existing plant. You have to get the existing plant SLD. Then you have to prepare the PV plant SLD, do the connection, and then go for the transient stability analysis. That means by creating different kinds of faults, like suppose line outages. Suppose a transmission due to three-phase fault happened in a OHL line over a transmission line which is at the PV plant end, because PV plant will be connected to the existing plant through transmission line. Suppose a three-phase fault happened at the transmission line, three-phase fault. Then what is its effect? What on the generators which are existing at the existing plant? Okay, so therefore you need to perform the rotor angle stability. That the rotor angle of the generators are within 0 to 90 degree or not. That you need to check it. So when the three-phase fault happened, and at what time you are removing the fault, when you are clearing the fault. That means critical clearing time of the critical clearing time we are calculating. What the CCT, fault clearing time, when the three-phase fault has happened at a transmission line, then at what time we should remove the fault so that the generator will not get unstable. Okay, so that is called critical clearing time. So that by conducting the test by using Dixelant Power Factory software or ETAP software, you can determine what should be the clearing time when a fault happened. At what time your breaker has to open so that the fault will be removed from the system. When the fault is cleared, so that time will be decided by conducting this test, transient stability analysis test. That's why we are conducting transient stability analysis, to know what should be the time of operation of the breaker, and this time of operation will be utilized in a relay coordination also. So all are interlinked. So whenever you are clearing the fault, at what time we need to clear the fault so that the generators at the existing plant will get stable, it will not get unstable. So what should be the clearing time? That will be decided, that will be determined by conducting this test. So that's why we are conducting transient stability analysis whenever you are connecting the grid solar PV plant to a existing plant. But when you are connecting the solar PV plant, yeah, am I audible?
Yes, yes,
Hello.
yes,
Okay.
yes.
So this is about the transient stability. Just in briefly, I'm telling, and under dynamic study, LVRT, HVRT test will come into picture, and due to shortage of time, just in briefly, I will tell you, low voltage ride through, high voltage ride. This is the most important task performed whenever you are going for the grid integration, PV plant connection to the grid. Okay, LVRT and HVRT test, low voltage ride through and the high voltage ride through test. Because when there is a fault happened at the grid end, the voltage will goes down. If the voltage will goes down, your plant should not be disconnected from the grid. Okay, So then collapse may happen. So therefore, at up to what time you should have to be there in connected with the grid, so that is specified by the CA. And within that time, what is happening into the plant in the grid, PV plant, and at the grid end, that we have to analyze. Okay, so therefore we are conducting LVRT and HVRT test, low voltage right through and high voltage right. These are fault right through test conducted, and which are coming under the grid compliance study. Okay, so this is grid impact study, and then grid compliance study is there. That means you have to follow the CA regulations. Okay, so that is LVRT and HVRT test. And then last one is protection coordination studies. As I said, that means protection coordination studies is nothing but you have to set the relays in a PV plant. The relay or circuit breaker has to be coordinated in a the sequence of operation will be there. Okay, so that set time has to be coordinated for reliable operation of the PV plant during fault situation. When there is a fault happened, at what point it has happened, and which part of the network has to be disconnected for smooth operation of the rest part of the system. It is not that the major part of the network will get disturbed due to a fault happened at one point. So that a engineer has to look into matter that how to coordinate the protecting devices in a PV plant when it is connected to the grid. Okay, so that is nothing but the protection coordination studies. It is a huge study. Many more things are there, but due to time constant, I'm explaining. But this is one of the grid impact studies. All these studies are coming under the grid impact studies, and we have to perform for the uh, to get the approval for the interconnection. And these are the final grid compliance study report needs to be submitted. List of test or study reports are required to be submitted by RE generators whenever you are going to install the PV plant before interconnection. All these report has to be approved. Okay, in compliance to CA regulations on technical standards for connectivity to the grid. Power quality test already discussed. Harmonics current injection at PY, DC current injection at PY, flicker injection at PY. These three reports we need to produce. Then a reactive power capability test, PQ capability test, VQ test, those things has to be submitted and verified and get approved. Then voltage right through, LVRT, HVRT, just now I have told you. These are all called a grid compliance study. Must and should, you have to get it approved, all these reports. Then a frequency response test, that means within 49.5 to 50.5 Hz, you have to supply the contract demand at the point of interconnection. Okay, and then active power control set point. You can control the point of the active power at the point of interconnection. That control you must have according to the set point. You have to vary. And the ramping capability test. That means whenever suppose your generation is going down to a very low value, and then then whenever you are increasing it, then it has to follow a percentage of rate. It's not that at any percentage of you can change the active power to be injected to the network. So that these tests need to be conducted and submitted for approval. So these are the benefits of the grid impact studies. To ensure, the most important is ensures reliable operation of the power system and prevents costly outages or equipment damage. Obviously, because if you want to conduct this test, then if suppose some fault has happened, then it may damage the equipment also. Breaker rating, transformer rating, everything will be decided breaker rating will be decided based upon the short circuit current. So like that. So that's why and helps in designing appropriate mitigation measures. Example, reactive power compensation, grid upgrades. Reactive, what should be the size of the reactive power needs to be installed at the PV end. So that will be decided based upon the studies. That's why we are performing these studies. So the other references. Thank you.
Thank you, Dr. Sachidananda.
Thank you, sir.
I think we
Do you have
are
any
little
questions?
running out of time.
Yes,
Because there is a feedback and other things. Okay.
okay, sir. Okay.
So any questions from participants? If you have any questions, you can ask here.
Hello.
So,
Good
yeah.
afternoon. Good afternoon, all.
Yes, please go ahead.
Good afternoon, Sachidananda sir. I am Dr. Aditya Prasad Padi from Arkajan University.
Yeah, good afternoon. Good afternoon, please.
Sir, can you tell me what is the Dick silent application in power system load flow studies?
Dixilent is a power system tool we are using for conducting various tests like load flow analysis, short circuit analysis, and dynamic study also we are performing like reactive power analysis, and then transient stability analysis. All these studies were how ETAP is a software, how MATLAB is a software, similar Dixilent is a software we are using for conducting all these studies. And that software selection is based upon the grid code. Okay, so the based upon the in different country grid code, they will specify for which study, which software needs to be, the task has to be performed in which software. So some task you need to submit the report using a Dixilent software. So we are using and performing the test.
Okay, okay, sir. Can I incorporate renewable energy sources with the for load flow analysis?
Yeah, I just now what we conducted, what I have shown you, that is nothing but a PV plant connected to the grid. Okay, 10 megawatt PV plant connected to this. That means you can model a PV plant using Dixilent software, using ETAP software. Okay, so you can model.
Okay, okay, okay. Thank you, sir. Thank you.
Any other questions? Okay, Doctor, we are going to close this session because we have the validatory feedback, other things. Okay, thank you very much for detailed explanation on this topic. Okay,
Thank you,
with
sir.
teaching and both industry experience reflect over here.
Thank you, sir. Thank you for this opportunity, sir. I thank you for this invitation, and I got the opportunity to explore my knowledge with all of you. Thank you very much.
Thank you. So participants, now the time is for taking feedback. So I request some of the participants can switch on our video and give some feedback about our program. Yes, Krishna Rao. Yes. Please, anyone?
Hello, sir.
Dinesh sir, please. Your mic is off. It's on now.
Sir, am I audible, sir?
Yes, you are audible.
Okay, sir. So this is really a very informative session throughout, and we got the opportunity to hear from all about the researchers throughout the globe, not only from this country, and really many informations we got about the mitigations of these climate changes. And I'm very glad that now the research is not confined to only one domain. It has been so there is now marriage between different domains like electrical, electronics, computer science, and that is the real test that we can get the perfect solutions of the present trend, different problems. And so thank you very much, sir, for organizing this FDP. And we got a lot of constructive information, and we look forward to work on this. Thank you, sir.
Thank you, Dr. Dinesh sir. Next.
Can I talk here?
Yes. Mr. Chalakrishna. Your voice is not audible. It's not, your voice is not audible.
Hello?
Yes.
Am I audible, sir?
Yes, now you're audible.
Okay, thank you, sir. So, good afternoon, sir. This is Krishna Rao. As we conclude this enriching faculty development program on mitigating climate change through sustainable electrical engineering solutions, I am filled with a renewed sense of purpose and responsibility. Over the past 6 days, we have delved into the pressing issues of climate change, explored innovative solutions, and discussed strategies for integrating sustainability into our teaching, research, and practices. I would like to express my gratitude to the resource persons, organizers, and our institutes for providing with us this platform to learn, share, and grow. As electrical engineer, we have a critical role to play in mitigating climate change. I pledge to incorporate the knowledge and insights gained from this workshop into my academic pursuits to develop sustainable solutions. Thank you once again, sir. I wish you all the very best way in our collective efforts to create a more sustainable in future, sir. Thank you, sir. Thank you very much.
Thank you, Mr. Chalakrishna. Thank you for your comments.
Thank you, sir.
Yes. Next, anyone want to give this? Ranjan Misra, Mr. Ranjan Misra, you want to tell something?
Sure, should I?
Rajan Mishra.
Yes.
So the organization of the FDP, the faculties and the resource person, it was very good, and plus the way the topics are organized, let us learn a lot from them, and the research ideas they are providing, it is going to helpful throughout, like at least for the next 5 to 10 years. They have given a lot of research problems to work on in this field. So really, I'm really grateful for this faculty development program. Thank you, sir.
Thank you very much, Mr. Ranjan Misra. Mr. Shankar, you want to give any comment?
Sir, nice faculty development program, sir. I am doing also same work on research on climate change only.
You are from which
Dr.
place?
Vikram Kulakarni.
Okay. Very nice. Yeah.
Thank you so much once again, sir. Very nice for FDP.
Thank you. Dr. Subrajyoti Sarkar.
Thank you, sir, for giving me the opportunity to give the feedback at the end. It is overall a nice session. Unfortunately, I couldn't turn on my video as I used to roam all around, but I heard quite a few sessions, and it's very relevant actually to the recent work that are being going on around this. Overall, it's a very wonderful FDP, and almost all the sessions I had personally learned quite a lot of things, sir. Thank you, sir.
Okay. Thank you, Dr. Subrajyoti Sarkar. Shweta Panna, madam.
Yes, sir. Good evening, sir.
Good evening.
The 6 days FD was very informative and very helpful for me, sir. And it basically highlights the significance of renewable energy and energy efficient systems and smart grids in tackling the climate changes. And I would like to thank all the delegate speakers for the sessions. The sessions provided basically includes practical knowledges also. So at last, I would like to thank PMSC Electrical Engineering branch and as well as Sir Saurav sir and Sao sir for organizing this FTP.
Thank you, Shweta madam.
Thank you, sir.
Any other state from Kerala? Anyone? Because there are many state people joined this program from Kerala, Maharashtra. So Kerala, anyone? I'll check. I know some people in Kerala. Tejaswini Biswal. Yes, Satyajit Sahu, Mr. Satyajit Sahu. Please
Hello,
give
sir.
some comment.
Hello, sir. Good evening to everyone. Good evening to all the whole team of Sachidananda Engineering College, who has given us the opportunity to attend this 5 days program. So I just want to share some few takeaways what I have got to this faculty development program, sir. Sir, first of all, good evening to everyone. It's a privilege to be here today and sharing my thoughts on this Atal faculty development program, sir, on mitigating climate change through sustainable electrical engineering solutions. Basically, as an electrical engineer, we have a lot of options to tell the world about different alternatives that we have got and which can be used to mitigate climate change. And this 5 days FDP has actually been one of the eye openers for every one of us, that we as a teaching fraternity, we as professors, or we as electrical engineers have got a lot of thing to do in our hands for the future. If we can do a small part even, and if we can save our planet Earth from this climate change, it will be a very helpful, and I'll think that as an electrical engineer, I have given back something to the society. If I could have we could save some climate change effects that we are facing. So I just urge to everyone who is present over this faculty development program to actually take these takeaways and implement in our daily life, or maybe we can research on them further so that we can make our planet better, sir, for a better future. And thank you very much, Sarath sir and Saroj sir, for organizing this FDP. I guess there has been a very big preparation before this Atal program, because reaching to everyone and reaching to the speakers also would have been a very long task. We see this as a very easy Zoom meeting which everybody joins, but there have been a very big task at the back-end team, to the whole electrical engineering department of Parala Maharaja College of Engineering. I thank you very much, sir, and I wish that in future also we collaborate among ourselves and participate in further, sir. Thank you, sir. Thank you very much.
Thank you, Dr. Satyajit. I am expecting some other state people.
Hello, sir. This is Maitri, sir.
Maitri madam.
How are you, sir?
Video.
Sir, video, sir.
Yeah.
1 second, sir. Video. 1 second, sir.
Okay, no problem. You take your
Hi, sir. How are you?
I'm fine. How are you?
Yeah, fine, sir. Such a nice FDP, sir. So I would like to extend my heartfelt gratitude for the enlightening session on mitigating climate change, sir. So your expertise and the faculty expertise and thoughtful insights, practical approaches. So I think all this has empowered us to contribute the meaningful to addressing the global change. So, and also thank you for your for whole 6 days. You have been here for up to 10 o'clock, I think, for your dedication and for sparking the important conversation with us throughout the session, all the sessions. And also, I am looking forward for more such impactful discussion in the future also, sir.
Thank you, Dr. Maitri.
Thank you, sir. Thank you.
Thank you. Nice words. Next, from Kerala, we have people from Karnataka, Maharashtra, Andhra Pradesh, Telangana, Kerala, Uttarakhand, Rajasthan, Chhattisgarh, Bihar. Anyone from Kerala?
Sir.
Good evening, Srikant B.
Sir, this is Srikant.
Please switch on your video.
Yes, sir. I'm doing it.
Yeah.
Sir, very good evening, sir. This is Srikant.
Good evening.
So it is my pleasure to be part of this mitigating climate changes through sustainable electrical energy solutions, sir. And we have been in a big environment that for since 1 week we have been part of this FDP, and all evenings are been like that research environment, and the research the research which has been created till this week, sir. It is very wonderful, and it is a big opportunity for all the research scholars like me, and it created all the research gaps, and everyone gone through the research gaps and where we can apply our research things, and I am very thankful to Saroj sir and Sarath Kumar sir, and for giving this opportunity to be part of this FDP, sir. And I am waiting for the remaining all FDPs which are conducted by PMAC.
Okay. Thank you, Mr. Sirkan.
Thank you, sir.
Next. Anyone from Rajasthan? No one? Tensi Thomas, I think from Kerala. Tensi Thomas, Miss or Mr. I don't know. Tensi Thomas. Feel free, okay? Don't worry about the test. You are not there? Priti Mary Tom is there. Dr. Priti Mary Tom. He is there. Okay, then sir will go to. I want to give some instruction. After that, Saroj sir will give a vote of thanks. After that, we will close this session. So, in your Atal account, if you visit there, you can write the quiz over there. Okay. So, if it is active for you, you can attend the quiz from today night itself. So, there will be 30 questions. Each question carries 1 mark, and that is for 45 minutes. 30 questions, 45 minutes. So, 3 things to get the certificate from Atal FDP. First one, you have to qualify the quiz, that is 70% of the mark. Second one, your feedback. You have to submit the feedback in Atal. And the third is your attendance. So I have to update the attendance by today night or tomorrow evening, like that. Okay. So these 3 criteria, once you are fulfilling, you will get the certificate from Atal. So be careful while attending the quiz. You have enough time. Okay, 45 minutes is enough time. Only 30 questions are there. And I will also share one Google spreadsheet link today after this program in our WhatsApp group to give the feedback. Okay, because sometimes if you're they have given the instruction to us that feedback Excel sheet has to be uploaded. So that is separate. So that is the feedback from my end. Then your feedback you can give in Atal website. Okay, there are 2 feedback I am going to collect. And this online feedback also, this video feedback also they have asked. So that is why I have already taken this video feedback. So you have to give another feedback in Atal, and another Google spreadsheet link I will send through WhatsApp group by today night or after this program. So that is the thing. Then if there is any issue, like I'll share the attendance, whatever I'm going to enter all the 5 days attendance, I'll share in the WhatsApp group, because most of the people have seen they are not attending. They have joined the Atal in Atal website, but online sometimes they're attending, sometimes they're not attending, and strictly they are given the instruction that 80% of the time you should attend. Okay, so 80% if you are not attending, then you will not get the certificate. So I have taken the licensed version of the Zoom. Zoom is taking the attendance, and Zoom is giving one Excel sheet. Okay, how much time you have attended and how much time you have conducted the program. So based on that, I will enter that. If there is any mistake, anything, personally you can send a mail to me or you can WhatsApp me, sir, I have attended this time to this time. Then I will check through Zoom. If there is any mistake, I will correct that, and same attendance I will enter in the Atal website. Okay. So if your quiz link is not active, then you have to wait. Don't call or don't send message. By tomorrow you can wait. For one day you can wait for your quiz. But I think it will be active in your login. If it is active, you can attend the quiz today night or by tomorrow anytime. Okay. If there is any issue, you just send a message. Please don't call, send WhatsApp message, not in the group. If it is in personal, any problem, you can send personal WhatsApp message, or if any serious issue, you can call me. Okay. Anything else? You have any clarification, any doubt?
No, sir. Thank you so much.
No, sir. Thank you.
So I request all of you, you please switch on the video, because I have to share a screenshot to AICT also with the video. So please switch on the video. I want to take a screenshot of that. Thank you. Thank you very much. I have taken the screenshot. So now I request Dr. Saroj Kumar Pradhan to give the vote of thank. Okay.
Thank
Please,
you,
sir.
sir. So, good evening, dear participants. Myself, Dr. Saroj Pradhan, co-coordinator of this FDP. So it is both an honor and a privilege to deliver the vote of thanks as you conclude this intellectually enriching one-week online Atal faculty development program on mitigating climate change through sustainable electrical engineering solutions. So on behalf of the Department of Electrical Engineering, PMEC Berhampur, I extend my deepest gratitude to our distinguished speakers. Your expertise, thought-provoking insights, and willingness to share your knowledge have significantly elevated the quality of this event. Your contributions have provided us with a renewed perspective and actionable takeaway that will undoubtedly guide us in our professional journeys. Participants are joined from different states of India, that is from Odisha, Karnataka, Tamil Nadu, Maharashtra, Andhra Pradesh, Telangana, Kerala, Uttarakhand, Rajasthan, Chhattisgarh, Bihar, etc. So participants, your active engagement, thought-provoking questions, and meaningful contributions have been pivotal in making this FDP a grand success. Your enthusiasm to learn and exchange ideas has made this platform vibrant and productive. So lastly, a special note of appreciation goes to the technical and administrative teams. Your meticulous attention to detail and seamless coordination ensured that the virtual platform operated smoothly, so providing an excellent experience for all attendees. So as we conclude, let us take a moment to reflect on the wealth of knowledge shared during this program. So let us strive to apply these insights and continue to build bridges of collaboration and innovation in our respective domains. So thank you all for your participation, dedication, and most important, your valuable time. So wishing you will continued success in all your future endeavors. So thank you all.
Thank you, sir.
Thank you, sir.
So we'll play the national anthem. After that, we'll close the session. Whether my screen is visible, sir?
Yes, sir, visible.
So I request all of you, please stand for the national anthem. Thank you, all of you. So for quiz, you can visit the link. If you are facing any issue like your questions are now, I have already uploaded, but due to attendance or since I didn't enter the attendance, it may show that quiz is not uploaded, something like that. So you have to wait because it is active till 24 hours. Okay. Thank you. Thank you very much. We'll leave the meeting.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you. Thank you very much.
Thank you very much, sir.
Thank you. Thank you, madam.
Thank you, sir.
Thank you.